All right, let's talk about one of the biggest secrets to GPU performance, something that can literally make or break your code. It's a hidden mechanism that separates the good from the truly great, and it's called memory coalescing.
So let's start with a problem that I'm sure you've felt before. You've got this incredibly powerful, expensive piece of hardware, but for some reason, it feels like it's completely stuck in a massive traffic jam.
It's a super frustrating question, right? You have thousands of cores just sitting there ready to crunch numbers, but your application is running way slower than you think it should. Well, the answer usually isn't about the cores themselves. It's all about how they get their data.
To really get what's going on here, let's use an analogy. Picture your GPU as this giant, high-tech factory. The thousands of cores, they're your workers on the assembly line. And the GPU's memory is a massive warehouse, just packed with all the parts those workers need.
Now, imagine if every single one of those workers needed, say, one specific screw, and each one of them individually walked all the way over to the warehouse to get it. You'd have chaos, right? The aisles would be clogged, workers would be just standing around waiting, and the whole assembly line would grind to a halt. That complete mess, well, that's exactly what an uncoalesced memory access is. It is the traffic jam.
So, how do we fix this disaster? Well, any good factory has a brilliant manager, someone who optimizes the whole workflow. And it turns out your GPU has one of these managers built right into the hardware, specifically to prevent this kind of chaos.
And that manager's name is memory coalescing. At its heart, it's the super smart hardware feature that sees all the individual requests coming from a group of threads, and if it can, it bundles them all up into one single hyper-efficient trip to the warehouse.
And the goal here isn't just about pure speed. It's about making the entire system efficient. The idea is to completely max out the data highway, make way fewer trips to memory, cut down the time threads spend just waiting for data, and, most importantly, keep those thousands of cores busy actually working.
So, how does this memory manager actually pull this off? Let's zoom in and follow one single data delivery to see how it all works.
It's really like a four-step dance. First, a whole group of threads, called a warp, all ask for their data at the exact same time. Then, the memory controller, our manager, looks at everyone's shopping list, all the memory addresses they need. Now, if it sees that all the parts they need are right next to each other on the shelf, meaning the memory is sequential and aligned, it merges all those requests. It sends one forklift to get one big box, brings it back, and then hands out the right part to each worker. One trip, maximum efficiency.
But, and this is the huge catch, if the data those threads need is scattered all over the warehouse, the manager can't do anything. It's forced to send everyone out on their own, separate, slow individual trips. The whole system bogs down, and performance absolutely plummets.
And this leads to a critical realization. The real power isn't just in the hardware. It's in how you, the developer, organize your data in that warehouse before the work even starts.
And for so many programmers, this is the big aha moment. It's the difference between an array of structures and a structure of arrays. With an array of structures, you might store an x and a y coordinate together in a pair. But think about it. When a group of threads all want just the x coordinate, they have to jump over every y to get to the next x. They're leaving these gaps, which completely breaks coalescing. But with a structure of arrays, you put all the x's together and all the y's together. Now, when the threads ask for the x-coordinates, the data is perfectly lined up one after the other. It's a single, beautiful, coalesced memory access.
So, to bring it back to our factory, choosing a structure of arrays is like you, the developer, pre-packaging all the screws in one box and all the bolts in another. You're lining everything up so the memory manager can just grab the whole pallet in one go. You're literally designing for efficiency.
Okay, so you do all this work. What's the payoff? Well, getting this right has a massive payoff, but it's also really important to know the real-world limitations.
When you achieve perfect coalescing, you set off this amazing chain reaction of good things. Traffic on your memory bus goes way down. You get much closer to your theoretical max bandwidth. Your threads stop waiting and start working. Your overall throughput just skyrockets. You even use less power to get the same work done. It's a win all around.
And I mean, that throughput improvement we're talking about isn't small. For applications that are bottlenecked by memory access, getting your data structure right can lead to performance gains of up to 10 times. Seriously, it can be the single most important optimization you make.
But let's be real for a second. This isn't some magic bullet that solves every problem. Some algorithms, like graph traversals, are just fundamentally random, and they're always going to struggle with coalescing. Restructuring your data can also sometimes make your code a bit more complex and harder to read. And to top it off, the exact rules for what counts as a perfect access can even change between GPU generations. So, as always, it's a trade-off.
So the next time you're trying to squeeze every last drop of performance out of that GPU, don't just stare at the algorithm. Take a look at your warehouse and ask yourself this one crucial question. Is your data structured for chaos, or is it structured for speed? The answer to that could be the key to unlocking the true power of your hardware.